In this video, we're going to take a look at balancing redox reactions. So we've already balanced reactions to satisfy the conservation of mass, to make sure the same number of atoms of each element is on both sides of the reaction and that nothing is created nor destroyed. But we also need to do that in terms of electrons. So when electrons are transferred from one substance to another to change the charge, have one thing reduced and the other oxidized, then the amount of electrons that are transferred also has to be equal. So we split into two separate half reactions, the oxidation reaction and the reduction reaction, and look at the amount of electrons that are transferred and make sure those balance. And this can be done in a neutral solution, in an acidic solution, or a basic solution. So let's take a look first at what it looks like to balance a neutral reaction. So when you balance a neutral reaction, first you're going to split them into, again, the two different half reactions, the oxidation half and the reduction half. And then determine the least common multiple of electrons that are involved between the two half reactions. Multiply both half reactions that is needed to get to that least common multiple. And then combine those two reactions together, and that'll give you a complete reaction. So let's take a look at what a neutral reaction looks like and how we're going to balance it in terms of electrons. So in this particular case, we have here calcium oxide and aluminum reacting in a single replacement reaction to make aluminum oxide and calcium. So calcium has a +2 charge being reduced to 0, and aluminum has a 0 charge being oxidized to a +3. So our two half reactions are aluminum, again giving up those 3 electrons, becoming oxidized, calcium taking on 2 electrons and becoming reduced. So the least common multiple of the 3 electrons and the 2 electrons is 6. So you have to multiply the aluminum reaction by 2 and the calcium reaction by 3. Now we have 6 electrons in total for both halves. And now we have, again, our aluminum giving up 3 electrons and 2 sets of them, so aluminum giving up 6 in total, to the calcium, which is now each taking on 2, so 6 in total there also, to be reduced back to its elemental state. So we know that we need 3 calciums and we need 2 aluminums. So now when we look at that top reaction, we find, well, I need 3 calcium oxides with 2 aluminums, which then gives me that 1 aluminum oxide and then 3 calciums to make it all balance out. So again, there's 6 electrons that are transferred in total. And in this particular case, if you balanced it in terms of atoms, it would have worked out okay, same way that it worked out here. But there are times when you do balance the atoms and it doesn't balance out the electrons. So now let's take a look at the steps that we're going to use to balance a redox reaction in an acidic solution. So first we're going to split them into the two halves still, our oxidation half and a reduction half. And then we need to balance all the atoms that are not hydrogen or oxygen to start. And then once you have those all set, then you can look at the oxygens, and because it's in an aqueous solution, there's water there. So we can use that water in this reaction. So we can add water to balance out oxygens, and then because of the hydrogens now added from oxygen and being an acidic solution, we have H+ ions, hydrogen ions, which can be added in to now balance out the hydrogens. However, the charge to start and the charge to finish on each side of the reaction, the reactants and the products, has to be the same. So now you're going to add in the electrons that are needed to make that balance. Then you can compare the two half reactions in terms of number of electrons, again finding that least common multiple, and then multiplying your two half reactions to get to that least common multiple. And then again combining those two reactions together to get your finished reaction, your end reaction. However, you do need to cancel out substances that appear on both sides. Those are just spectating. So now we'll take a look at how we actually balance in terms of electrons with an acidic solution. So we got this reaction here of copper with nitrate making nitrogen dioxide and a copper 2 ion. So we have our copper being oxidized, losing 2 electrons, and we have our nitrate ion being reduced from a +5 when it's in the nitrate ion to a +4 when it's in the nitrogen dioxide. So the first thing we need to do is balance these in terms of the amount of elements that are not hydrogen and oxygen. And for the copper one, well, there is no hydrogen or oxygen there, and the copper is already balanced, so we actually don't have to do anything to that reaction at all. So then looking at the second reaction, our reduction reaction, well, we have 1 nitrogen on the reactant side and 1 on the product side, so those are good. So now we can move on to the next step where we're going to balance out the oxygens. So So we have 3 oxygens on the reactant side, we have 2 on the product side. So we need to add a water molecule, again, because it's in an aqueous solution. So adding 1 water molecule gives us 1 more oxygen, so now we have 3 and 3. However, that did give me now 2 hydrogens. And since there's 2 hydrogens that are there on the product side, I need 2 more on the reactant side. So I can add 2 hydrogen ions to the reactant side to make those balance. And then lastly, we need to balance the charge of the 2 sides. Well, again, on the reactant side, I have 2 hydrogen ions and I have a nitrate ion. We'll come back to those in a second. And on the product side, we have no charge on nitrogen dioxide, no charge on our water, so it's neutral overall. So we need to get to a neutral overall charge on the reactant side. Each hydrogen being a +1, I have 2 of them, gives me +2 from the hydrogens, but only a -1 from the nitrate. So I need to add 1 electron to the reactant side to give that an overall charge of neutral. So now I can compare my oxidation reaction with my reduction reaction and make sure the amount of electrons are balanced. Well, in the oxidation reaction, I have 2 electrons. In the reduction, I only have 1. So the least common multiple between those is 2. So the copper reaction, once again, we can leave alone. However, the nitrate reaction down below, we do have to multiply by 2 and double it up. And then that'll give me the 2 electrons I need to balance out my 2 half reactions. So here I see my nitrate ion multiplied by 2, my number of electrons. Again, I have 2 of them. I have 4 hydrogen ions now, and I have 2 nitrate ions. I can then combine them together, and I see that reaction down below, where I have copper plus 4 hydrogens, making the 2 nitrates with 2 electrons, producing 2 nitrogen dioxides, 2 waters, the copper, 2 ions, and 2 electrons. So really all that's here to simplify and eliminate as a spectator is these 2 electrons. So my final reaction is my copper plus the 4 hydrogen ions with the 2 nitrate ions, producing the 2 nitrogen dioxide molecules, 2 water molecules, and the copper 2 ion. So now to do a basic reaction, it's very similar, except we don't have hydrogens to use, but we're going to start with hydrogens anyway. So you're still going to separate them into 2 different half reactions, and then again balance and do everything else you would throughout the acidic process. So balance the non-hydrogen oxygens, and then come back and balance the oxygens, then balance the hydrogens, balance the electrons, and then make sure you get the least common multiple of electrons and make sure those all balance. But then from there, again, we don't have hydrogen ions that which you can use. So we can't have hydrogen ions in our reaction, but it's basic. So we have hydroxide ions. And so if I add a hydroxide ion with a hydrogen ion, I get a water molecule. And again, water we have. So now all we need to do is add equal amounts of hydroxides to each side of every reaction that has hydrogen ions involved, to then get rid of the hydrogen ions, giving us water, and then giving us hydroxide ions, which are there in a basic solution. And then you can simplify the 2 half reactions, combine them together, and again, using the least common multiple of electrons, make sure they all balance. And then lastly, combine those together, again, canceling out the substances that appear on both sides of the equation. So take a look at how that works. We're going to use the same reaction we already had and pick up where we left off. So again, we went through all the steps, we balanced out the non-hydrogen oxygens, we balanced out the oxygens, we balanced out the hydrogens, the electrons are all there, everything's good to go. However, at this bottom reaction, again, we have these 4 hydrogen ions, which we can't have because this is a basic solution. There aren't hydrogen ions to be used in a basic solution. So in order to get rid of those 4 hydrogen ions, I can add 4 hydroxide ions to each side. Because when I combine the 4 hydrogen ions with 4 hydroxide ions, I'm going to make 4 water molecules. And now I have 4 hydroxides again on the other side because you can't add it to one and not the other. And then now here's my final reaction, and all I have to do now is simplify those that are on both sides. Those are just spectating. So I do have 4 water molecules now that are reacting. I have 2 water molecules that are being produced. So I can just say 2 water molecules reacted, and then I have my end product here of my copper with the 2 water molecules, the 2 nitrate ions, making 2 nitrogen dioxides, the carbon 2 ion, and the 4 hydroxide ions.